Okay, thanks, Peter, and thanks to the organizers for inviting me to speak today. So today I'll be talking about some joint work with Jim Geelen and Peter, and this is not yet posted to the archive, but pretty much everything I'll talk about today is in my thesis, which you can find online at the Waterloo Thesis Repository. Okay, so here's the plan for this talk. There's two parts. I'll first tell you our motivation for working on these problems, and then I'll tell you our main result, which has to do with group labeled graphs. And in the second half of the talk, I will tell you about how we can apply our main result to some nice classes of representable and algebraic matroids. Okay. So I'll start with the following natural question. Given a class M of matroids, what is the maximum number of elements of a simple rank n matroid in the class M? So an answer to this question provides some important information about this class, and maybe that information could be useful as well. And it's natural to encode an answer to this question as a function called the extremal function. So the extremal function of a non-empty class M of matroids is the function which takes in a non-negative integer n and outputs the maximum number of elements of a simple matroid in the class of rank at most n. Okay. And the matroids in the class which meet the bound given by this function are called extremal for this class M. Okay, so I'll just go through some examples to make sure we all understand what this function is doing. Okay, so first note that if M contains all rank 2 uniform matroids, then this function is actually not well defined for all n at least 2, because a simple rank 2 matroid can have arbitrarily many elements. Okay, so that's if that happens, we just define this function to be infinite for those values of n. Okay, so this is not great, but luckily there are many nice classes of matroids which do not contain all rank 2 uniform matroids. For example, the extremal function for the class of binary matroids is 2 to the n minus 1, because a binary matrix with at most n rows has at most 2 to the n minus 1 distinct non-zero columns. Okay, so that gives an upper bound, and that bound is attained by binary projective geometries. So projective geometries are extremal for the class of binary matroids. Okay, another natural class, the extremal function for the class of graphic matroids is n plus 1 choose 2, because a simple graph on at most n plus 1 vertices has at most n plus 1 choose 2 edges, and equality is attained by cliques. Okay, so cliques are extremal for the class of graphic matroids. And one last example, the extremal function for the class of planar graphic matroids is 3n minus 3, because a simple planar graph on at most n plus 1 vertices has at most 3n minus 3 edges by Euler's formula, and equality is attained by planar triangulations. Okay, so these are some nice examples of extremal functions, and these classes are all examples of minor closed classes of matroids. Okay, and we can see that the functions in these examples are very different, right? We can see this function could be infinite, exponential, quadratic, or linear in n. Okay, so this leads to the following question: which functions can be the extremal function of a minor closed class of matroids? Okay, so this is our first motivating question. And this question is broadly answered by the growth rate theorem. So here's what the growth rate theorem says. It's a combination of several papers by various subsets of these authors, Geelen, Cabell, Kung, and Whittle. And it says that if M is a minor closed class of matroids, then there's some constant C depending on the class, so that either the class M contains all rank 2 uniform matroids and the extremal function is infinite, or there's some prime power Q, so that the extremal function is exponential with base Q, and M contains all GFQ representable matroids, or the extremal function has a quadratic lower bound and upper bound, and M contains all graphic matroids, or the last option, the extremal function has a linear upper bound. Okay. So this theorem says that the behavior illustrated by those 4 examples on the previous slide, that's essentially all that can happen up to this constant. So this theorem broadly answers question 1. So that's great. However, it'd be even better if we could answer question 1 precisely. So precisely which functions can be the extremal function of a minor closed class of matroids. And using the growth rate theorem, we can ask this question separately for classes of type 2, 3, and 4. And those classes are called base Q exponentially dense for classes of type 2. Classes of type 3 are called quadratically dense, and classes of type 4 are called linearly dense. So now I'll just kind of quickly go through and tell you what's known about the extremal functions of classes of type 2, 3, and 4. Okay, and I'll start with linearly dense classes. Okay, so here's an example of a nice linearly dense class. The class of graphic matroids without the cycle matroid of K33 as a minor has this extremal function. It's 3n minus 2 whenever n is equivalent to 1 mod 3, and 3n minus 3 otherwise. So there's this periodic behavior that depends on the value of n. And it's conjectured by Geelen, Harrods, and Whittle that this is always the case, that if M is a linearly dense minor closed class of matroids, then the extremal function is some linear function plus a periodic function, where all the terms are rational numbers. Okay. And this has been proved in some special cases, but it's hard in general. And that's one reason it's hard is because the extremal matroids do not have to be highly connected in any sense. So in this example, when n is equivalent to 1 mod 3, you can construct an extremal matroid for this class by just taking 2 sums of the cycle matroid of K5. Okay, so that's one example of extremal matroids for this class. And that makes it a bit tricky to prove things about the extremal functions for linearly dense classes, as we'll see a bit later. Okay, so that's the situation for linearly dense classes. For exponentially dense classes, the story is quite different. So Jim and Peter were actually able to completely characterize the possible extremal functions for exponentially dense minor closed classes. Okay, so here's what they proved. If Q is a prime and M is a base Q exponentially dense minor closed class of matroids, then there are integers K and C, so that the extremal function for M is precisely this function whenever n is sufficiently large. So that's about as good of a result as you could hope for in terms of answering question 1. And we would like to prove an analogous result for quadratically dense classes. Okay. So here's what's known for quadratically dense classes. It's not much at the moment. For example, this conjecture of Geelen, Harrods, and Whittle is wide open. If M is a quadratically dense minor closed class, then the extremal function is eventually some quadratic polynomial. Okay, so that's not known. And certainly to answer question 1 for quadratically dense classes, we would have to first prove or disprove this conjecture. Okay, but this one reason this conjecture is tough is the following. So if you give me some quadratically dense minor closed class, I would first have to prove that there's some upper bound on the extremal function, which is actually a quadratic function, and then I would have to exhibit a class of matroids which meet that bound, and that's tough. It's these extremal matroids in general might not be so easy to describe. Okay, so that's why this is hard. However, that does lead us to another question, which we can use kind of as a first step towards this conjecture. And maybe this question is a bit more open-ended. Okay, so here it is. What are the extremal matroids of quadratically dense minor closed classes? Right, so we have to be able to answer this question in order to prove this conjecture. But we can maybe give a approximate answer. So it's a bit open-ended. Okay, so that's the main motivating question for the research that I'll present in this talk. So are there any questions so far? Okay, so now I will show you two nice examples of quadratically dense minor closed classes for which the extremal matroids exhibit very different behavior. And this will kind of illustrate why this question is tough to answer in general. And both of these examples will come from group labeled graphs. Okay, so the first class is called the gamma frame matroids. So given a finite group gamma, a gamma frame matroid is the frame matroid associated with the graph whose edges are labeled by elements of gamma. Okay. So we don't need a precise definition for this talk. We just need some properties of this class. So first, when the size of gamma is 1, this is exactly the class of graphic matroids. Okay, so these matroids generalize the graphic matroids. And second, it turns out that each simple rank n gamma frame matroid is a restriction of a matroid called the Dowling geometry of rank n over the group gamma. So it's denoted dg and gamma. Okay, so to show you what these gamma frame matroids look like, I just have to show you what these Dowling geometries look like. So here's an example of a Dowling geometry. This has rank 4, and this is over a group of size 5. And this matroid has the property that it has a basis, in this case B1, B2, B3, B4, so that for each pair of basis elements, the number of other elements that they span is equal to the size of gamma. Okay, so the size of gamma is 5, and there's 5 points here, and 5 points between each pair of basis elements. Okay. And right, we can compute the extremal function for this class by just counting the number of elements of these Dowling geometries. Okay, so the class of gamma frame matroids has extremal function given by the size of gamma times n choose 2 plus n. And that's just because this matroid has a basis of size n, and for each of the n choose 2 pairs of basis elements, the number of other elements that we get is equal to the size of gamma. Okay, and I just want to point out the structure of these gamma frame matroids. Right, there's quadratically many of these lines of length at least gamma, and these lines are kind of spread out in this clique-like structure. And by that I mean that you can take if you take a matching of basis elements, that will give you a large collection of mutually skew lines of length equal to the size of gamma plus 2. So these lines are kind of spread out. Okay, so that's the first example of a nice quadratically dense minor closed class. Here's the second, the gamma lift matroids. Okay, so again, these coincide with the class of graphic matroids when gamma is trivial. So I'm just going to define these when the size of gamma is at least 2. So a gamma lift matroid is the lift matroid associated with the graph whose edges are labeled by elements of gamma. And again, I just want to show you what these matroids look like. Okay. And again, each simple rank n gamma lift matroid is a restriction of a matroid we call the lift geometry of rank n over the group gamma. And we denote it by LG and gamma. Okay, so here's what these matroids look like. Okay, they have an element E, so that if you contract E and simplify, you end up with the cycle matroid of the clique K sub n. Okay, so these matroids are one contraction away from a clique. And each line through this element E has size equal to the size of gamma. Okay, so in this example, this is a lift geometry of rank 4, right? Because K4 has six elements, and the size of gamma is 4 because each of these lines has length 4 plus 1. Okay, and I'll just say that technically this is a complete lift matroid in the notation of Zaslavsky because we're including this extra point E. Okay, but I'll just call them the gamma lift matroids. Okay, and the class of gamma lift matroids has extremal function given by the size of gamma times n choose 2 plus 1, because there's n choose 2 of these long lines, and each has the size of gamma points other than E. And the point here is that these lift geometries look very different from Dowling geometries, because all of these lines of length at least gamma go through this common point E. Okay, so every pair of these long lines is coplanar, and this is behavior very different from the Dowling geometries. Okay. So to determine the extremal matroids and quadratically dense classes, one thing we can do to deal with these two different types of examples is we can say, let's try to disallow the behavior exhibited by these gamma lift matroids. And then maybe we can show that the extremal matroids must be Dowling geometries, or at least close to Dowling geometries. Okay, so that's what we did, and that's our main result. So we show that if M is a quadratically dense minor closed class of matroids, which contains no rank K lift geometry over a non-trivial group, then there is some group gamma and a constant C, so that the extremal function of the class M is the size of gamma times n choose 2 plus some linear term, and M contains all gamma frame matroids. Okay, so if we exclude all lift geometries of some fixed rank over a non-trivial group, then the extremal matroids are close to being Dowling geometries. Okay. So this is nice because it shows some sort of relationship between these two natural classes of matroids associated with group label graphs. But there's maybe two potential drawbacks. The first is that it's unclear whether it's even possible or common for a quadratically dense class to actually exclude all lift geometries of some fixed rank K. Okay, so maybe that's tough for natural classes. And second, this is not an exact result. We have this linear error here. Okay. So for the second half of the talk, I will show you that we can actually apply this result to find the exact extremal function for some natural classes of representable and algebraic matroids. Okay, so before I move on to the second half, are there any questions?
I guess I have a question. So is there a bound on that constant?
Yeah, so it's some, in this case, it's some explicit function of constants given by your quadratically dense class. So it's some function of K and the length of the line that you exclude in your class, and a couple other things as well. Yeah, but it's an explicit constant. Okay, so I'll move on to some applications of this result. And I'll first show you how we can use our main result to get a more exact result. Okay. So the reason this result is not exact is because this class of matroids M, it could contain a Dowling geometry over gamma plus some extra element. So it could definitely contain extensions, simple extensions of Dowling geometries. So that's why we can't get an exact bound here. So if we want to get an exact result, we're going to have to exclude extensions of Dowling geometries. Okay, so I will write dgr gamma plus e to denote any simple extension of this rank r Dowling geometry over gamma with rank r. So this element e is not parallel to any element of the Dowling geometry, and it's not a loop, and it's not a co-loop. Okay. So here's what we get if we exclude these matroids. We show that for all integers L, K, T, and R, if M is a minor closed class of matroids, which does not contain the length L plus 2 line, then either it contains some rank K lift geometry over a non-trivial group, or it contains a simple extension of a rank R Dowling geometry over a group of size at least t, or the extremal function is upper bounded by t times n choose 2 plus n for all sufficiently large n. Okay, and the reason this is nice is because if this class M does happen to contain Dowling geometries over a group of size t, then those matroids will meet this bound. Okay, those Dowling geometries would be extremal for this class M. So our goal is to try to apply this theorem to some class M for which these first two outcomes do not hold, and which contains Dowling geometries over a group of size t. Okay, that would allow us to find the exact extremal function for M. Okay, so now I will show you that there are many nice classes of representable matroids for which these first two outcomes, in fact, do not hold. Okay, so here's one connection between these Dowling geometries and lift geometries and representable matroids. Okay, so here's a key proposition. For each integer L at least 1, if M is a matroid with no length L plus 3 line as a minor, so that either M is a rank 3 lift geometry over a non-trivial group, or M is a simple extension of a rank 3 Dowling geometry over a group of size L, then M is not representable over fields of characteristic 0, and is representable over fields of at most one positive characteristic. So the representability of these matroids is very restricted. And here's the reason why. It's not hard to show that each of these matroids has a Reed geometry restriction, which we denote Rm, which is representable over a field F if and only if F has characteristic M. Okay, so that was proved by Reed. And I'll just show you what these matroids look like. So when M is a prime P, this Reed geometry RP is just a specific restriction of the projective plane over the field of psi with P elements. So, for example, when M is equal to 2, this Reed geometry is just the Fano plane, and you can generalize that construction to any integer at least 2. Okay, and I'll just mention briefly that this proposition also holds if you replace the word representable with algebraic. Okay, so I won't define algebraic matroids, but the point is that's a stronger result, because if a matroid is representable over a field, then it's also algebraic over that field. And the proof is the same, and it turns out that this Reed geometry Rm is algebraic over a field F if and only if F has characteristic M. And that was proved by Gary Gordon. So the results that I'll show you also hold for algebraic matroids. Okay. So here's the connection between our matroids of interest and representability. So now we can combine this with our exact result to get some corollaries. Okay. So here's kind of a more specific statement of our exact result, just in the case where these matroids have rank 3. And okay, so first we can apply this to a field of characteristic 0, such as the complex numbers. Okay, So we prove that for each integer L at least 1, the class of complex representable matroids without the length L plus 3 line as a minor has extremal function precisely L times n choose 2 plus n whenever n is sufficiently large. Okay, so why does that follow from this theorem? Well, as we saw on the previous slide, these first two outcomes are not representable over fields of characteristic 0. So these first two outcomes do not hold. And therefore, this theorem gives us an upper bound of L times n choose 2 plus n. And it turns out that we get a matching lower bound because Dowling geometries over the cyclic group of size L are complex representable. Okay, so Dowling geometries are extremal for this class. Okay, and this was conjectured by Peter and also by Rohan Kapadia. Okay, and we also have a corollary for fields of positive characteristic. So we'll let F1 and F2 be finite fields of different characteristic so that the size of F1 minus 1 divides the size of F2 minus 1. Then the class of matroids representable over both fields has extremal function given by the size of F1 minus 1 times n choose 2 plus n for all sufficiently large integers n. And this follows from our exact theorem for the same reason. These first two outcomes are not representable over fields of different characteristic, as we saw on the previous slide. Therefore, this theorem gives us an upper bound. And again, it turns out that that Dowling geometries over the multiplicative group of F1 meet that upper bound. So those Dowling geometries are extremal for this class. And that's why we need this divisibility condition. So that's what allows these Dowling geometries to also be representable over F2. Okay, and this was conjectured by Joseph Kung and also by Geelen, Herards, and Whittle. And this was already known in two important special cases. So when F1 is equal to GF2, this is just the class of regular matroids. And when F1 is equal to GF3, this result follows from a combination of several papers. But this was open in all other cases. Okay, so hopefully I've convinced you that this exact theorem is interesting, and for the remaining time, I'll just give a brief sketch of how the proof goes, and I'll focus on how our main result is used in the proof, because I think that's not entirely clear. And I'll also focus on how these lift geometries and Dowling geometries come up in the proof. Okay, so here's the exact result, and we're going to assume that this third outcome does not hold. So we'll suppose that the extremal function is greater than L times n choose 2 plus n for infinitely many integers n. Then we'll try to find one of these excluded minors. Okay, so from here there's two main steps, and these steps are not unique to this particular proof. They've been used many times in the past, mostly by Jim and Peter. So I'll try to indicate which parts of this proof hold more generally. And I'll try to give a sense of what kind of techniques go into proving an upper bound on the extremal function for some minor closed class. Okay, so all we're assuming is this density condition that that matroids of arbitrarily large rank have more elements than L times their rank choose 2 plus their rank. And it turns out that we can get quite a lot from just this assumption. Okay, so here's the first step. We show that there is some vertically 15 connected matroid M in the class, which has a rank R for some large integer R, Dowling geometry minor over a group of size L, and it has some restriction, which is non-Dowling. So by non-Dowling, I just mean that this restriction is not a restriction of any Dowling geometry. And if you aren't familiar with vertical connectivity, that's not important. What is important is that this matroid has some nice connectivity property. Okay, so here's the picture. We have this matroid M, the ground set of this minor, and this non-Dowling restriction X. And we would like to contract some elements to realize this minor G, and while preserving the set X. Right, then since this restriction is non-Dowling, that would give us the second outcome. It would give us a simple extension of a Dowling geometry. Okay, so that's a bit too much to ask for, but here's what we can show. We can find some minor n with a spanning Dowling geometry restriction G prime over gamma, and we can recover some subset X prime of X so that n restricted to X prime is non-Dowling. Okay. So then this picture just gives us the second outcome. Okay. And I'll point out that this only works because of this connectivity condition from step 1. Because if the ground set of G and X were, say, in different connected components of M, then we would have no hope of contracting them together. Okay, so the first step, we exploit this density assumption to find some structure, and in the second step, we exploit this connectivity to kind of push these structures together. Okay, so now I'll just kind of go through each of these steps and say why we can get these properties, because that's not clear. Okay, so all we have to start with is this density assumption, and first we get some matroid which is vertically 15 connected. Okay, so why is that true? So that's essentially true because quadratic functions with positive leading coefficient are convex up. So if you have some matroid with greater than this many elements, and it has some small separation, since x squared plus y squared is less than x plus y squared, whenever x and y are large enough integers, you just can't have a matroid with this many elements with a small separation. And this is a more general property of quadratically dense minor closed classes. You can always find extremal matroids which are arbitrarily highly vertically connected. That was proved by Jim and Peter. But we just need vertical 15 connectivity for this proof. Okay, the second the second property is that M has this large rank Dowling geometry minor over a group of size L. And I think this is maybe more surprising, because this is almost what we're looking for, right? We want a Dowling geometry restriction over a group of size L plus some extra element, and this minor gets us most of the way there. So why can we assume that M has this minor? Well, this is where our main result comes into play. Okay, so our main result says that this class M has some associated group gamma, so that M contains all gamma frame matroids. If we take this group gamma to be as large as possible, then it must have size L. If it has size less than L, then our main theorem gives an upper bound on the extremal function of L minus 1 times n choose 2 plus some linear term. And that's just too small. Okay, so this class M contains all gamma frame matroids over some group of size L. And that's certainly a key step in our proof, is making sure we have this minor. Okay, and third, I have to tell you how we find this non-Dowling restriction X. Okay, so first we find some element E, so that when you contract E and simplify, you lose lots of elements from your matroid M, roughly L times the rank of M. And this element E, it's not hard to find. You can just take M to be minor minimal with respect to this density, essentially. And then it turns out that just this density assumption on E can get you a lot of structure. So here's what we prove. This gives a non-Dowling restriction, which either has rank at most 15 or is a spike. So I'll define what a spike is on the next slide. But the point is that this restriction either has bounded rank, which makes it nice to work with, or is a specific matroid. It's a spike, and spikes have some nice properties that we can exploit. Okay, so this is nice because we get all of this just from this density assumption. Okay, and now we've reduced the proof to just a problem about vertical connectivity and spikes. Okay, so here's what a spike is. A simple matroid S is a spike if it has some element E, so that the simplification of S contract E is a circuit, and each parallel class of S contract E has size 2. Okay, so it's kind of two copies of a circuit. So we've now reduced the proof to this following proposition. Okay, we have some vertically 15 connected matroid, which excludes the length L plus 3 line as a minor, and excludes all rank 3 lift geometries over non-trivial groups as minors. Then, if M has a large rank Dowling geometry minor G over a group of size L, and a spike restriction of rank at least 5, then M has a minor with a spanning Dowling geometry restriction G prime over gamma, and a spike restriction of rank 5. And the reason we have this rank 5 condition is that spikes of rank at least 5 are non-Dowling. Okay, so that's key. We're not happy with a spike of rank 3 or 4. So here's the picture. We have this minor G, and we have some enormous spike, and we want to find this minor N. with a spanning Dowling geometry restriction G prime, and we want to recover some part of this original spike. And I'll just point out why this is tricky. So this Dowling geometry minor G, it's associated with some contract set. And if that contract set contains the tip of this spike, then we could be in trouble. Because if we want to realize this minor, then we're going to destroy our spike. Okay. And that, to get around that, that's where these lift geometries come into play. So we show that we can either find a large Dowling geometry restriction, or we can find a lift geometry minor over a non-trivial group. So those lift geometries allow us to move from a minor to a restriction, and then the problem is much easier. You can apply theorems like Tutt's linking theorem from there. Okay, so that's all I want to say about the proof. Hopefully this gets you interested in trying some extremal matroid theory. And I'll stop there. Thanks for listening.
Thank you, Zach. Are there any questions?
Yeah, my question is, you look at all possible single element extensions of Dowlings. Is it possible to restrict to certain special single element extensions of Dowlings?
Yeah, that's a good question. So if you just look at the case where your Dowling geometry is a clique, then Jim and Peter proved something like that. That if you have a large rank clique, a large rank single element extension of a clique, then you can find some big rank simple extension of a clique where that extension has one of three types. So you could probably prove a similar thing for Dowling geometries, although it would be messier.
Thanks. And the result about quadratically dense, the conjecture that Jim and Bert and Jeff have, it says for real numbers A, B, and C. I mean, is it really going to be all real numbers? What possible numbers are going to show up there? I mean, are you going to get non-rational numbers?
No, they should probably end up being half integers. And yeah, but that I don't think that's been explicitly conjectured anywhere as far as I know.
Thanks.
Yeah, maybe the leading term is all that needs to be a half integer. Like it's really kind of A times N choose 2 plus B N plus C, where A, B, and C are integers. That'll be my guess. Maybe that's equivalent. Any more questions? If not, then thank you again. I'll stop the recording now.